Colligative properties. Have you ever made ice cream at home? And you have to put salt on the ice or it just doesn't work. Do you know why you add salt? It makes the temperature of the ice colder. It seems kind of weird, doesn't it? Isn't ice cold? Well, ice is cold, but when you put salt on it, it gets colder. Ice melts at 0 degrees Celsius. If you put salt in it, it'll melt at about -10 degrees Celsius. That's significantly colder. That's a property called freezing point depression, and that's what's known as a colligative property. Colligative properties depend on the number of particles that are dissolved. They don't depend on the type of particle. So this is kind of an odd set of properties because usually, properties depend on what kind of a substance you have dissolved. Colligative properties of electrolytes are going to be slightly different than non-electrolytes because electrolytes separate into multiple particles. So 1 mole of an electrolyte, like sodium chloride, is going to make 2 moles of particles. 1 mole of calcium chloride is going to make 3 moles of particles because it separates into calcium and 2 chloride ions. Whereas if you have something like sugar, which dissolves in water just fine, 1 mole of sugar makes 1 mole of particles. So what are these properties? One of them is vapor pressure lowering. We've talked about the concept of vapor pressure. We get a dynamic equilibrium between evaporation and condensation. We have a beaker with a watch glass over it to keep the gas from escaping. Well, when we put a solute into this solution, now the solute occupies some of those spaces near the surface and interferes with the evaporation of the liquid. If the rate of evaporation is lower, then when this comes to equilibrium, the pressure of that substance in the gas state will be lower. Lower vapor pressure because the solute molecules interfere with the evaporation of the solvent. Does that make sense? So that's kind of a simplistic explanation. It's relatively easy to understand, but that doesn't really explain this phenomenon. So here we have, looks like a cake plate, doesn't it? 2 beakers, 1 pure solvent and 1 a concentrated solution. So maybe this is water and this is salt water. If you leave this over a fair period of time, what will happen is that some of this solvent will move to the other beaker. Right? Like, what? If I could, hold a thought in my head long enough, I'd try this at home, but I always forget when I get home. This actually has to do with entropy, nature's tendency toward mixing. So here we have a pure solvent, here we have a concentrated solution. Nature's tendency towards mixing and spreading out energy is going to cause the solvent to move from one beaker to the other. And it's not magic or anything. Solvent evaporates from this beaker, solvent evaporates from that beaker. This is a closed system, and so solvent will condense into this beaker and condense into that beaker. And we'll see a rise in the level of liquid in the beaker that has the solute in it. Any questions? We can quantify this. Ralts Law is used to quantify vapor pressure. The vapor pressure of a solution is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. So if you have pure solvent, then the mole fraction would be 1 times its pure solvent vapor pressure, and pressure of the solution will be the same as. But if you have the more the less solvent you have, because you're essentially diluting it by adding solute, the lower the pressure of that solution will be. So the vapor pressure is directly proportional to the amount of solvent in the solution. Your book goes through this derivation. We can look at the vapor pressure lowering, delta P. We can derive it from this statement up here. Delta P is going to be the mole fraction of the solute times the vapor pressure of the pure solvent. So the more solute you have, the larger the change in the vapor pressure. Here's an example. And here we're talking about non-electrolyte solutes and non-volatile solutes. Because if it's volatile, that adds another layer. And then if it's an electrolyte, we have to consider the number of particles. So these are not electrolytes, just to keep things a little simpler. So calculate the vapor pressure at 25 of a solution containing 55.3 grams of ethylene glycol and 285.2 grams of water. The vapor pressure of pure water is 23.8 torr. So if we want to know what the vapor pressure of the solution is, we need to use Ralts Law. So the vapor pressure is going to equal the mole fraction of the solvent times the vapor pressure of the pure solvent. So we need to know the mole fraction and the vapor pressure of pure water. Well, the vapor pressure of pure water is given to us right here. We're given masses of ethylene glycol and water. Water here is going to be the solvent because there's a lot more of the water than there is of the ethylene glycol. Ethylene glycol is also a liquid at room temperature. So we need to take these two masses and convert them into moles and find the mole fraction. So we need the mole fraction of H2O, and that will equal the moles of H2O divided by the moles of H2O plus the moles of, we'll call it EG. So 285.2 grams of water. So we have the mass of water, and we need to use the molar mass to convert to moles. It'd be really great if it would show on the screen what I'm writing on the iPad, but that apparently would be too much to ask for. So we need to take the mass of water and divide by the molar mass to get the number of moles of water. So it's 15, 4 sig figs there, 8269 moles. And then we need the moles of ethylene glycol. So we've got 55.3 grams. And let's see, 1, 2, 3 carbons times 12.01 plus 2 oxygens times 16 plus 2, 4, 6, 8 hydrogens. 8 times 1.008. 76.094. Anybody else get that molar mass? Thanks. 55.3 divided by 76.094. So we've got 0.72673 moles of that. So we'll plug the number of moles into our equation for the mole fraction. And then in the bottom we have the sum of the two. Plus 0.72673. The denominator, we're still going to have 4 sig figs, so we don't need to worry about that. So we have 15.8269 divided by the quantity 15.8269 plus 0.72673. Get a mole fraction of 0.956098. And that has no units. So this mole fraction then comes up into Ralts Law, where it's the mole fraction of the solvent, that's what we calculated, times the vapor pressure of the pure solvent. Vapor pressure of the pure solvent is 23.8 torr. So the vapor pressure of this solution is 22, it should have 3 significant figures, 22.8 torr. The vapor pressure of the water is lower because there's ethylene glycol in it. Any questions? What if we have a volatile but non-electrolyte solute? When the solute is volatile, it contributes to the vapor pressure. Remember, a volatile substance is one that evaporates easily. So now we've got the vapor pressure of the solvent, and we also have a vapor pressure from the solute. So this makes things a little more complicated. When things are, when we have an ideal solution, that will follow Ralts Law at all concentrations for both the solvent and the solute. And here things are fairly simple. The total pressure above an ideal solution is just the sum of the partial pressures of the components. Of course, you think ideal solutions are normal? No, probably not. Nothing's ever ideal, is it? We encounter non-ideal solutions quite frequently. Non-ideal solutions don't follow Ralts Law because of interactions between the solute and the solvent molecules. If those interactions are extra, particularly strong or particularly weak, then things become a little different. So let's look at this. So in this graph, we have vapor pressure increasing on the y-axis, and we have the mole fraction of component A increasing as we go across to the right. So if we look at the partial pressure of component A, where its mole fraction is 0, its vapor pressure is 0. And as it increases linearly until we get to its pure vapor pressure at a mole fraction of 1. The vapor pressure of B is in blue, the partial pressure. When the mole fraction of A is 0, the mole fraction of B is 1. And so its vapor pressure is equal to the pure vapor pressure. And it decreases linearly to 0. For a mixture, you just add the two vapor pressures, and we also get a straight line. That's an ideal solution. If we have strong interactions between the solute and the solvent, do strong interactions within the solution cause higher vapor pressure or lower vapor pressure? Lower vapor pressure, right? It's harder for the molecules to break free. So when there are strong interactions between the solute and the solvent, then we see a bowing in these lines, and it goes below what is expected. So the vapor pressure of component A is lower than expected, except where the mole fraction is 1 and the mole fraction is 0. Because at that point you have a pure substance, either A or B, and there's no interactions. And for component B, we also see this dip. And so the vapor pressure for the total solution is still the sum of the two individual pressures. But here we see a deviation. Ralts Law predicts this straight line, and it dips significantly below that. And the maximum effect is where you have roughly equal molar quantities of the solute and the solvent. If we have especially weak solute-solvent interactions, you can almost think of them like wanting to get away from each other, right? The solute and the solvent are like not mixing up very well. And so they're like, I really want to escape into the gas state. It's better out there. I can get away from you, right? And so we see an increase in vapor pressure for each component. And then when we add those together, we get this higher than expected vapor pressure for the solution. Does that make sense? We're not going to do calculations with that, thankfully, but we need to be aware of the phenomenon. Let's look at this. A solution of benzene and toluene is 25% benzene by mass. The vapor pressure of pure benzene and pure toluene at 25 degrees Celsius are 94.2 torr and 28.4 torr, respectively. Assuming ideal behavior, calculate the following. The vapor pressure of each of the solution components in the mixture. So we want to know what's the vapor pressure of the benzene and what's the vapor pressure of the toluene. What equation are we going to use to find that? Ralts Law. So the pressure, I'm going to call benzene Ben. The partial pressure of the benzene will equal the mole fraction of the benzene times the vapor pressure of pure benzene. And likewise for toluene. So we're going to need mole fractions. Well, we've got this 25% benzene by mass. So 25% benzene. That means there's 25 grams per 100 grams, right? So I'm going to say, well, let's just pretend that it weighs 100 grams. Then I know I have 25 grams of benzene, and I must have 75 grams of toluene. With masses, I can calculate numbers of moles. So I'm going to say we've got 25 grams of benzene, and then we want to find the number of moles of benzene. So I did some of these calculations ahead last night, because this one's a bit of a booger. So we can calculate the molar mass of benzene. I got 78.108. And that gives us a number of moles of 0.32007. That's moles of benzene. Then I must have 28 grams of toluene. I'm going to call him tol. I calculate the molar mass of toluene. Correct me if you find any mistakes. I got 92.134 grams per mole. And doing the math there, I get a number of moles of 0.81403 moles of toluene. So now we need mole fraction of benzene. The mole fraction of benzene, chi ben, is going to equal the moles of benzene, 0.32007 moles divided by the total number of moles. 0.32007 plus the 0.81403 moles. And that comes out to be 0.28222. That's the mole fraction for benzene. So then to find the partial pressure of the benzene, we take the mole fraction, 0.28222, and multiply by the vapor pressure of pure benzene, which is right here, 94.2 torr. So that comes out to be 26.585 torr. So that's one answer, vapor pressure of each solution. I'm not going to round that yet because we're going to need that for the next part. If you were just reporting that one, you'd say 26.6 torr. Any questions? If this is the mole fraction of benzene, what's the mole fraction of toluene?